Alright, welcome back everyone. This will be another episode of the mathematical playthrough. We are still on analysis, so let's just get into it. So today I wanted to prove, I think it's called the double or second derivative test. I'm not exactly sure if it's what it's called. I'm not pulling up my like the notes I have, lecture note for the course. I'm studying on analysis. You can call it calculus, I guess. It doesn't. So yeah, here we have example 2, how to sketch a graph using the information from second derivative. All right, I think we'll try to figure it out on our own before we actually get on. So I think it's called the second derivative. I'll just call it second derivative formula. We have a function that goes something like this. I guess a point here. How does it go? So we suppose that f continuous. I guess we could say that an f double prim exists if f double. I think it's something to do like with f double. If f double prim is positive, then we know that f is concave or something. We can think of this as being negative, but it is increasing to become positive, right? So I'm guessing the second derivative on this point is gonna be positive, right? Here we see that we have the inflection point here. At a positive angle, it's becoming more and more negative. So I'm guessing at this point it's positive and at this point it's negative. We know that if this double prim is positive, we know that this is concave, right? And then the second case is if f double prim is negative, then f is convex. Let me just check so I gotten this convex and concave down. Alright, so we have a concave and then we have convex, right? So concave is like a cup and the convex is like the other side of the cup, right? Alright, that makes sense. I think this is how you formulate it, but let me actually check if this is correct. We have the second derivative. So here they go through the convex and concave. We have a happy function. So here is the second derivative test. Suppose f is twice differentiable on AB, has stationary point at C A of B, then it holds that local minimum. And if f double prime is equal to 0, then anything can happen. It could be an extreme point or it could be an inflection point. Alright, so I guess a more correct statement would be that f is continuous on AB. I guess we don't need the endpoints. We have the derivative and double derivative exists, and we also have that we have a stationary point which is also within the same interval. So we have a point C here. If we have f of C, yeah, I guess that would be a good thing to also mention here. We have f of C convex. Let's see if this aligns again. Right. So it's even deeper like that. So it is a stationary point. Well, that's interesting. Right. All right. So I guess I was wrong again with saying this. So we're gonna do if f double prime of C is greater than 0. So then f is min point, local min, and then this is local max. So how do we prove this? Well, how do we do this? I don't know if I've convinced myself that this is actually true. If we have a point here, then the double derivative of this point is also bigger than 0. But since this point is not a stationary point, i.e. a stationary point meaning that the derivative of C is equal to 0. Because this is not a stationary point, we know that this is not a local max, right? Or a local min, I mean. Yeah, sorry. But if we do know it's a stationary point, we have a different situation. So anyways, I guess in the original statement, we only need to know that it's twice differentiable on AB, which I guess makes sense. We don't need to know that it's continuous. because we don't need that information when doing the proof. We can restate this. F is twice differentiable on AB. So for example, we have AB here, we have A here, and maybe we have B here. I don't know the proof, right? But I think we can get to the proof fairly easily based on the other proofs I've done. Here we know that we have a stationary point at C, which is in AB. So we know that f of C is equal to, the derivative of this is equal to 0. We'll do case 1. So we want to prove that f is a local minimum, and we want to do so by saying that if this is the case, then this. So let's try to take it into what we do know. So we do know this, and we do know that by the definition of the derivative, we know that we can write following. All right, we know that this is true, so this will be 0. We know that this is not 0. All right, I think I've found something actually. So we can rewrite this as being the limit as h goes to 0 plus on the positive direction. So we can think of a function. Maybe we'll do like this. We can think of, we're going to C here. This is the positive direction. We're going from a positive number to here. We can also go through a negative direction. Actually, I'm joking. This is gonna be 0. From this is positive 0 and this is negative 0. So what we can do here is we can just rewrite this. And now we do know the sign of h. So what do we know by everything here? So we know that C plus H. I'm not really sure what we know about this sign here, but I guess from first case here, we know that all this is equal to positive, and we know this is positive, which we can say that this implies that f prim C plus H is a positive number, and we can get this by multiplying H over here to this side, multiplying there. And then we know h is positive, so if h is here, we can type that this is bigger than this. And then we can use the axiom for inequalities to get this statement. And we can also say here that if this is positive, which it is, we know that f of prim of C plus H. I'm not sure if this is, it feels like I'm doing the same thing, but whatever. I think we can just consider one side, actually. Let's see if this leads to something interesting. Right, so we know that, actually, I guess we know that this, let me just think for a moment. How will I prove this? What does it mean by being a local minimum? If it's a local minimum, I guess we know that the stationary point, I guess the point is a stationary point. But what makes it different from a local max? I'm not sure if I have the mathematical muscles to prove that, you know. Do I prove it's a local min by showing that everything, ooh, yeah. So by showing that everything to the right of the point is positive, and by showing that everything to the left of it is positive, yeah, this is how we do it. And this is exactly what we get. Right, exactly. Right, so we can actually write this down to be more concrete. By showing that everything to the right is positive, and left is positive, we know C is local min, at least. It could be maximum, so that's kind of a big find. And this is exactly what we have here. I mean, this is true. So what have we proven now? So we've proven that on both sides, it is always positive, or it is always bigger than 0. But at C, it is 0. I think we're done here, honestly. Thus, C is local minimum. Yeah, we're just done like that. That was kind of fun. Hope you guys enjoyed that. We'll check the results now. Proof on the lecture note. This proof is actually kind of fun and kind of similar to that of Fermat's theorem above. Suppose we are in situation 1. Our first observation is that x is equal to C is a stationary point for f. F double prim of C is equal to the limit as x goes to C, f prim of x minus f prim of C is equal. Okay, so this is kind of interesting. So he does like my approach, the approach I did. So instead of writing down the definition of limit as this, he writes this down as, this is another way to write the definition of the derivative. Probably everyone knows this, but I think it's interesting. Let's move on with the proof. And then he simplifies, because we know this is 0, he simplifies this as being this. Now we proceed by considering the one-sided limit separately. Exactly. We do this in order to get the fact that f double prim C is less than 0 into play. So he did So what is confusing me is that he's saying that f double prime of c is less than 0 into play, but he's proving case 1 where he knows f double prime of c is greater than 0, whatever. Here the denominator must be positive, right, since it's going from a larger c value to a c, so it must be positive. But since the fraction is supposed to be negative, this means that f prime has to become negative as x goes to it. For similar reasons, yeah, so he actually did a typo here. He's not proving this case, he's proving the second case. So this is supposed to be I2 there, but whatever, let's move on. This means that fc has to become negative as x goes to positive c. For these reasons, f prime of x has to become positive. Yeah, for similar reasons. So he's looking at when x goes to the negative version of c. Exactly, and we're done. So yeah, this is actually the correct proof. He did prove the other version. He proved this version, but it's the exact same logic. So yeah, this was the proof of the second derivative. I did formula, but he actually, my professor is saying that it's second derivative test. So we'll go with the second derivative test. Alright, thanks everyone for watching. I'll see you in the next one.